This section is 1.5, and we're going to talk about functions and their rates of change. Now, when we first want to talk about increasing and decreasing functions, we're going to let f be defined over an interval L. So I'm going to pick some interval on a line, and x1 and x2 are in L. So I'm going to take some points in my interval. Then f increases on L whenever x1 is less than x2. Then f of x1 is less than or equal to f of x2. I know this may sound like Greek right now, but I'm going to give the formal definition here. On the next slide, I'm going to explain it in much simpler terms. F decreases on L1 if whenever x1 is less than x2, then f of x1 is greater than f of x2. Well, what does all this really mean? Well, in layman's terms, if I look at a graph and I move from left to right on the graph, that's what it means by x1 is less than x2. I'm going to start with a number less than another number, so I'm going to move from left to right. Then if the graph goes up, in other words, if f of x1 is less than f of x2, so in other words, this y value is less than the next y value, then the function is increasing. Here's an example that as I move from left to right, the function increases. In other words, the y values go up. That's simply what it means for a function to increase, is that when we look at a function from left to right, it goes up. However, if the graph goes down, in other words, if the first y value, f of x1, is greater than the second value, y value, x of x2, the function is decreasing. So in other words, if I move from left to right, and my function goes downward, it's said to be a decreasing function. Let's look at an example. Determine the intervals where the function is increasing or decreasing. This is actually the function f of x equals the absolute value of x. Notice that this function decreases for all values of x less than or equal to 0. So this function goes down from left to right for all these x values. And then once it hits the origin, the value increases for all the x values greater or equal to 0. Please note that when we're talking about intervals of increasing and decreasing, we're talking about x values, not y values. And please understand that a function can both increase and decrease on various intervals. It doesn't have to increase everywhere. This is a good example of where it decreases on one interval, then it increases on the next interval. I look at another example. This is f of x equals the cube root of x. Notice that this increases everywhere. As I go left to right, this function gradually increases. Even though it may level out some, it's still increasing as I'm going left to right. So this increases for all values of x. Well, how do we denote these values? We usually use what's called interval notation. This denotes specific intervals on the graph or the number line. For an interval notation, we need to remember certain things. The interval has two endpoints. The smaller endpoint is always listed first. That's followed by a comma. Then that's followed by the larger endpoint. For an interval that never ends, we introduce the concept of infinity. It's denoted by this sideways looking 8 here. And please understand that infinity is not a real number. It's simply a concept. You never reach infinity. Now we have these two numbers separated by comma. We also use either parentheses or brackets. We have to determine what to use for which occasion. Parentheses are called open intervals, and they're used to denote an interval where the endpoint is not included. Please note that everything up until the endpoint, including all the decimals, are included. And please note that you always use parentheses when using infinity. You never use brackets. Now brackets basically mean almost the same thing as parentheses, except that we include the endpoints. Let's look at some examples. The interval, we have an open parentheses, negative infinity to 5, close parentheses. That means everything to the left of 5, including 5, is included in this interval if I were to look at a number line. If I have another example, negative 2, comma, infinity, open parentheses on both ends, that means everything to the right of 2, but not including 2. If I have negative infinity to infinity, that simply means the entire number line. And I don't actually have to have infinity on one of these ends. I could have an example, close parentheses, a bracket, 1, comma 4. That means everything between 1 and 4, but it doesn't include 4. However, it includes everything up to 4, so 3.1, 3.8, 3.99999, etc. It does not just count the integers, it counts all the decimals, the rationals, irrationals as well. Let's define what average rate of change means. For a function f, and I have two distinct points, x1, y1, and x2, y2, the average rate of change of f from x1 to x2 is simply delta y, y2 minus y1, over x2 minus x1. Again, if we look at this, this is basically the same definition as slope between the 2 points. So when I'm talking about average rate of change, I'm literally referring to slope. Now, not all functions have constant slopes. If we look at this function f of x, okay, this does not have a constant slope. We're going to introduce the concept of the difference quotient, which is f of x plus h minus f of x all over h. In other words, I'm basically going to take 2 points. Instead of saying x1 and x2, I'm going to take x, and then I'm going to take some small distance h between them. So this is x and x plus h. So I'm going to use this notation instead of x1 and x2. If I were to do my slope calculation, or my average rate of change calculation, we'd have y2 minus y1 over x2 minus x1. Well, y2 in this case, instead of x2, I had x plus h. So instead of y2, I'm going to have f of x plus h. So that's where my f of x plus h comes from. Instead of x1, I had x. Instead of y1, I had f of x. There is my y1 there. Now I had x2 minus x1. Again, x2 was just x plus h. x1 was just x. Notice my numerator stays the same, f of x plus h minus f of x. And notice in the denominator, the x cancels and you're just left with h. Therefore, your difference quotient is just an average rate of change. And that's what you're really finding is the average rate of change between these 2 points on the secant line that connects them. Let's look how this works. If I have a function f of x equals x squared minus 2x, I want to find the different quotient of x and simplify. So I have f of x plus h minus f of x all over h. When I evaluate this function for x plus h, I'm going to put in x plus h everywhere I see an x. So this is x plus h squared minus 2 times x plus h. This is what I have here, x plus h squared minus 2 times x plus h minus, remember I put everything in brackets. I could use parentheses as well. Brackets mean the same thing when I'm trying to separate functions. Minus x squared minus 2x. So I'm going to square x plus h squared. This gives me x squared plus 2xh plus h squared minus 2x minus 2h when I distribute this negative 2. Then I distribute this negative sign into here. Negative x squared plus 2x. Now I need to cancel. X squared minus x squared cancels. Negative 2x plus 2x cancels. That leaves me with 2xh plus h squared minus 2h, which is what I have left in my parentheses. Notice they're all divisible by h. This simply leaves me with 2x plus h squared over h is h, minus 2h over h is minus 2. So our final answer is 2x plus h minus 2.